Welcome to The Explainer. I am so incredibly excited you're joining us today because we're about to go on a fascinating journey to completely demystify the mechanics behind the artificial intelligence we all chat with every single day. We're going to look right past that incredibly convincing, human-like interface of modern AI and dig deep into the actual math and engineering that's driving the whole shebang.
Okay, let's dive into this. If you spend any time at all online, or even just playing around with tools like ChatGPT, you have almost certainly felt it. You know, that undeniable, frankly, kind of eerie feeling that the conversational AI on your screen actually possesses a mind. I mean, search queries asking are LLMs conscious are spiking massively right now, and if you go on Reddit, the forums are just flooded with screenshots of AI acting so fluent and so incredibly empathetic that users are completely convinced there is someone or something thinking on the other side of that screen.
But to really understand what's going on here, we have to talk about anthropomorphism. This is our innate, deeply wired human tendency to assign human traits, emotions, and intentions to completely non-human systems. You see, when an AI is highly fluent, it triggers these powerful cognitive shortcuts in our brains. When a system perfectly mirrors our tone, remembers the context of our conversation, and spits out perfectly structured, calm responses, well, our brain instantly flags that as intelligence. We end up projecting our own emotions onto what is, in reality, just a highly structured language generation engine. So to start tearing down this illusion, we actually need to look at how an AI ingests human text in the first place.
Section 1. Breaking language into tokens.
So the very first thing to wrap our heads around is that AI absolutely does not read words the way you and I do. Instead, it uses this fascinating, greedy compression algorithm, usually something called byte pair encoding or BPE, to quite literally turn text into math. Here's how it works. The algorithm starts with just individual characters. Then it looks at massive, and I mean massive, training data sets to count adjacent character pairs. It finds the most frequent pairs, merges them into new symbols, and then just repeats this process over and over again until it hits a specific target vocabulary size. It is literally slicing human language into these weird numerical chunks.
And this example brilliantly illustrates the result. Just think about the word unhappiness. To a human being, that is a single, cohesive concept describing a very specific emotional state. But to the AI tokenizer, it gets chopped up into three completely distinct statistical subwords: un, happy, and ness. The entire system relies solely on these statistical chunks. You have to remember, AI does not think like humans. It predicts the most likely next token based on patterns learned from enormous amounts of data. It is completely devoid of human comprehension. So, okay, we've got our numerical chunks, but how do these chunks actually form those coherent, context-aware sentences that feel so real? Well, let's explore the core engine.
Section 2. How AI pays attention.
Before these tokens can even start to interact with each other, they have to become geometry. The model actually takes those raw numerical tokens we just talked about and transforms them into what we call embeddings. These are dense vectors that plot the token in a massive, high-dimensional space based purely on its statistical meaning. And then it adds positional encodings on top of that, which basically tells the model exactly where that specific token sits within the sequence of a sentence. So what we're left with is a geometric point for every token that represents both its semantic meaning and its physical location.
Once we actually have that geometry in place, the true magic of the transformer architecture kicks in. This is the attention mechanism. And honestly, the absolute easiest way to grasp this is to think of it like a giant database lookup, using Q, K, and V. For every single token, the model essentially asks three things. What am I looking for? That is the query. What do I expose or contain? That's the key. And finally, what is my actual payload? That's the value. Every single token compares its query against the keys of all the other tokens to figure out what's mathematically relevant, and then it pulls in the corresponding values.
So the absolutely crucial takeaway here is this stark comparison. When a human reads, we are understanding intent, we're grasping deep meaning, and we are feeling the emotional subtext of the words. AI attention, on the other hand, is purely mechanical compute. It is literally just scoring token relevance using dot products and scaling it all with soft math. Again, AI does not think like humans. It just mathematically computes which parts of the input should influence the output the most. But as you might guess, doing this insanely complex math for every single word takes massive computing power. So how on earth does it work at such a huge scale without just grinding to a complete halt?
Section 3. Scaling the engine. The KV cache.
You see, text generation works strictly one token at a time. If the model had to go back and recalculate the keys and values for every single previous word in a massively long conversation just to predict the very next one, it would literally take forever. The brilliant solution to this is the KV cache. It essentially remembers all the past calculations. It stores the previously computed key and value vectors in memory so they can just be reused instantly.
Now, what's really interesting about this slide is the sheer mind-boggling scale we are talking about here. 43 gigabytes. That is the memory needed just for the KV cache of a Llama 3.1 70 billion parameter model when it's looking at a 128,000 token context window. To put that into perspective, this temporary cache takes up more physical memory space than the entire foundational weights of many smaller AI models. It is just a massive, memory-hungry prediction engine.
And because of that massive memory footprint, modern AI engineering has become absolutely obsessed with finding ways to shrink the cache. We see different variants being used now. There's multi-head attention, which is your heavy memory baseline. But then there's grouped query attention, which shares KV heads to magically create a 75% smaller cache. And even multi-head latent attention, which compresses the cache down into latent vectors. What this perfectly illustrates is that modern AI optimizations are entirely about mechanical efficiency and clever memory tricks. They are absolutely not about growing a bigger, more human brain. So, knowing all these underlying mechanics, how do we actually categorize these systems in the grand philosophical debate?
Section 4. Stochastic parrots, or AGI. We have two very extreme camps here. On one side, the skeptics call these models stochastic parrots. They argue the AI is just blindly generating the most likely next token based on its training data, with zero understanding. On the far other side, some enthusiasts claim that as these models scale up, they are developing AGI, artificial general intelligence, meaning they possess emergent human-like advanced reasoning. But based on the very mechanical evidence we've just unpacked together, both of these extreme viewpoints are actually pretty flawed.
Let's look at how this builds into something a bit more nuanced. If a large language model were truly just a blind parrot, it would always say 8 plus 3 equals 11. Why? Because that is by far the most statistically common string of text in its training data. But if you prompt the model to temporarily redefine addition as a plus b plus 1, it will actually output 12. It isn't just parroting, it's actively mapping complex token networks and dynamically adapting to the novel constraints you gave it in the prompt.
And that leads us to this perfect middle ground reality, which we can call context-directed extrapolation. AI is essentially an extrapolator. It uses the massive structural priors from its training data, but it uses your prompt, the context, to actively target and apply the relevant mathematical structures. It navigates these complex data patterns beautifully, but make no mistake, it is still entirely bound by statistical constraints.
So to summarize our core thesis today, let's pull back the curtain one last time. What does AI actually do? Well, it absolutely analyzes token patterns, it calculates probabilities at lightning speed, and it mimics emotional cues flawlessly. But what does it not do? It does not experience subjective states, it does not form beliefs, and it certainly does not perceive the real world. Remember, AI does not think like humans. It predicts the most likely next token based on patterns learned from enormous amounts of data. It operates 100% on the math of next token prediction.
Which leaves us with this final, really provocative thought to chew on. These models are only going to get better. The conversational memory will improve, the fake empathy will feel more and more natural, and the simulation of logic and reasoning is going to become absolutely staggering. As the interface of AI continues to perfect this simulation of a mind, will we as human beings even be able to resist the illusion? Or will we be able to remember the incredibly complex, completely unfeeling mathematical engine running quietly underneath it all? Thank you so much for joining me on this explainer. Keep asking those big questions, and I'll see you next time.